Your conscious experience, every memory you possess, every sensation you feel, every thought flowing through your mind at this very moment, might be nothing more than an elaborate illusion. The life you remember living, the relationships you cherish, the accumulation of knowledge and experience that defines your identity, could all be false constructs generated by a brain that materialized from random chaos just moments ago. This is not science fiction. This is a legitimate scientific hypothesis that has profound implications for our understanding of reality itself. In the vast emptiness of space, where quantum mechanics governs the behavior of particles, the laws of physics permit something extraordinary and terrifying: the spontaneous formation of a fully conscious brain, complete with artificial memories of an entire lifetime that never actually occurred. Consider the fundamental nature of consciousness itself. Your awareness emerges from the specific arrangement of approximately 86 billion neurons in your brain, each connected to thousands of others through synaptic networks of staggering complexity. The patterns of electrical and chemical activity across these networks generate your subjective experience of being you. But what if this precise neural configuration could arise not through biological evolution and development, but through pure statistical chance? The mathematical reality is that given sufficient time, vastly longer than the current age of our universe, random quantum fluctuations in the vacuum of space could, theoretically, assemble particles into any conceivable arrangement. Among these possibilities lies the formation of a human brain, functionally identical to your own, carrying what appears to be a complete set of memories spanning decades of experience. This hypothetical brain would exist for only the briefest instant before thermal fluctuations caused it to dissolve back into chaos. Yet during that fleeting moment of existence, it would experience consciousness indistinguishable from yours. It would possess memories of childhood, education, relationships, and every significant moment you believe you have lived. The profound philosophical question becomes, how can you verify that you are not such a brain? The concept of a Boltzmann brain represents one of the most intellectually challenging thought experiments in modern physics and cosmology. Named after the Austrian physicist Ludwig Boltzmann, this hypothesis describes a hypothetical self-aware entity that emerges spontaneously from random particle fluctuations in a universe that has reached thermal equilibrium, a state of maximum entropy where energy is distributed uniformly throughout space. To understand the scientific foundation of this concept, we must first examine the statistical nature of thermodynamics. In any physical system, particles are constantly in motion, colliding and interacting according to the fundamental laws of physics. While the overall behavior of large numbers of particles follows predictable statistical patterns, individual particles behave randomly. This randomness creates the possibility for unusual configurations to occur, though with vanishingly small probability. A Boltzmann brain would form when quantum fluctuations in the vacuum spontaneously organize particles into the precise arrangement necessary to create a functioning brain. This brain would possess not only the physical structure required for consciousness, but also the specific neural states that encode memories, knowledge, and personality. The critical insight is that such a brain would be indistinguishable from a brain that developed through normal biological processes. The mathematical framework underlying this hypothesis relies on the principles of statistical mechanics. In a universe at thermal equilibrium, every possible configuration of matter has some finite probability of occurring, no matter how astronomically small. Given infinite time, even the most improbable events become inevitable. The formation of a single brain requires fewer particles arranged in a specific configuration, compared to the formation of an entire ordered universe containing stars, planets, and biological evolution. This comparison reveals a disturbing implication. Statistically speaking, it should be more likely for a brain to form spontaneously with false memories of observing an ordered universe than for such an ordered universe to actually exist. The ramifications of this statistical argument challenge our most basic assumptions about the nature of reality and the reliability of our observations. The Boltzmann Brain hypothesis transcends academic curiosity to become one of the most fundamental challenges facing modern cosmology. Its implications extend far beyond theoretical physics, touching the very foundations of scientific methodology and our understanding of existence itself. From a cosmological perspective, the hypothesis serves as a critical test for theories about the universe's structure and evolution. Any cosmological model that predicts Boltzmann brain should vastly outnumber normal observers, faces what physicists call the Boltzmann brain problem. If such brains are statistically more probable than naturally evolved observers like ourselves, then we would expect to be such brains rather than biological entities. The fact that we observe a consistent, ordered universe spanning billions of years contradicts what Boltzmann brains should experience. This contradiction has led cosmologists to reject or modify theories that produce excessive numbers of Boltzmann brains. Models of eternal inflation, certain interpretations of the multiverse, and scenarios involving infinitely old universes all fall under scrutiny when evaluated through this lens. The hypothesis thus functions as a filter, helping scientists distinguish between viable and problematic theoretical frameworks. The epistemological implications prove equally profound. If we were Boltzmann brains, our memories and perceptions would be fundamentally unreliable. The scientific method itself would become meaningless, as our observations would reflect random neural fluctuations rather than actual physical phenomena. This creates what philosophers term cognitive instability, a scenario where our methods of acquiring knowledge cannot be trusted. Furthermore, the hypothesis raises essential questions about the nature of consciousness and identity. If a randomly formed brain can possess consciousness identical to that produced by biological evolution, what does this reveal about the nature of awareness itself? Does consciousness require a particular physical substrate, or can it emerge from any sufficiently complex information processing system? The practical implications extend to how we evaluate scientific theories and make predictions about the future. Theories that imply we are likely to be Boltzmann brains create a paradox. They use the scientific method to reach conclusions that undermine the validity of the scientific method itself. This self-defeating nature provides a philosophical argument for rejecting such theories, independent of their mathematical consistency. Understanding why the Boltzmann brain hypothesis matters requires recognizing that science is fundamentally about making sense of our observations. If our observations cannot be trusted because they might be the product of random neural activity in a fluctuation brain, then the entire edifice of scientific knowledge becomes questionable. The hypothesis, therefore, represents not just a technical problem in cosmology, but a challenge to the coherence of rational inquiry itself. The resolution of this paradox has shaped modern cosmological thinking in profound ways. Scientists now routinely consider whether proposed theories produce acceptable ratios of normal observers to Boltzmann brains. This consideration has influenced models of dark energy, theories about the universe's ultimate fate, and our understanding of the anthropic principle, the idea that the universe must be compatible with the existence of observers like ourselves. As we proceed through this investigation, we will discover how this seemingly abstract thought experiment has become one of the most important conceptual tools in modern physics, guiding our understanding of everything from quantum mechanics to the ultimate nature of reality itself. The concept of a spontaneously formed brain materializing from chaos may sound like science fiction, yet it emerged from the rigorous mathematical framework developed by one of physics' most brilliant and tormented minds. Understanding this paradox requires examining the life and work of the Austrian physicist, whose statistical interpretation of thermodynamics inadvertently gave birth to one of cosmology's most perplexing thought experiments. Ludwig Eduard Boltzmann entered the world in 1844 in Vienna, Austria, during an era when physics stood at a crossroads between classical mechanics and emerging atomic theories. His childhood coincided with the Industrial Revolution's peak, a time when steam engines dominated technological advancement, yet the fundamental nature of heat and energy remained mysterious. The scientific establishment of the mid-19th century largely rejected the atomic hypothesis, viewing matter as continuous rather than composed of discrete particles. Boltzmann's genius manifested early in his academic career at the University of Vienna, where he studied under Joseph Stephan, a physicist whose own work would later contribute to our understanding of thermal radiation. However, Boltzmann's true intellectual breakthrough came through his revolutionary approach to understanding the relationship between microscopic particle behavior and macroscopic observable phenomena. While his contemporaries focused on deterministic equations describing individual particle trajectories, Boltzmann recognized that such calculations became impossibly complex when dealing with the astronomical numbers of particles present in even the smallest visible samples of matter. His solution proved both elegant and radical. Instead of tracking individual particles, Boltzmann developed statistical methods to describe the collective behavior of large ensembles of particles. This approach, now known as statistical mechanics, provided a bridge between the microscopic world of atoms and molecules and the macroscopic world of temperature, pressure, and other thermodynamic quantities that engineers and scientists could directly measure. The mathematical framework Boltzmann constructed rested on probability theory applied to physical systems. He demonstrated that temperature, previously understood as a fundamental property of matter, actually represented the average kinetic energy of randomly moving particles. Pressure resulted from countless molecular collisions against container walls. These insights transformed abstract statistical concepts into powerful tools for predicting and explaining physical phenomena. Boltzmann's work extended beyond mere calculation. He provided a mechanistic explanation for the second law of thermodynamics, showing how the statistical behavior of particles naturally leads to entropy increase. His famous equation S equals K times the natural logarithm of W, where S represents entropy, K is Boltzmann's constant, and W denotes the number of possible microscopic arrangements consistent with a given macroscopic state, established entropy as a fundamental measure of disorder at the molecular level. Despite the mathematical rigor and explanatory power of Boltzmann's theories, the scientific community of his era received his work with skepticism and often outright hostility. The opposition stemmed from fundamental philosophical disagreements about the nature of reality and scientific explanation. Ernst Mach, a prominent physicist and philosopher, led the charge against atomic theories, arguing that science should only concern itself with directly observable phenomena. From Mach's perspective, atoms and molecules remained unobservable hypothetical constructs that violated the principles of empirical science. The debate between Boltzmann and his critics transcended mere academic disagreement. It represented a clash between two worldviews about the purpose and methods of scientific inquiry. Boltzmann advocated for a realist interpretation of scientific theories, arguing that successful mathematical models reflected underlying physical reality, even when that reality remained beyond direct observation. His opponents, influenced by positivist philosophy, insisted that scientific theories should merely organize and predict observable phenomena without claiming knowledge of unobservable entities. Wilhelm Ostwald, another influential critic, promoted energetics as an alternative to atomism. Ostwald argued that energy, rather than matter composed of atoms, should serve as the fundamental concept in physics. This position gained considerable support among German-speaking physicists, creating an intellectual environment hostile to Boltzmann's atomic interpretations of thermodynamics. The personal toll of these professional battles weighed heavily on Boltzmann's mental health. Contemporaries described him as suffering from severe mood swings, alternating between periods of intense creativity and deep depression. The constant need to defend his theories against prestigious opponents, combined with the slow pace of experimental confirmation of atomic theories, created a sense of intellectual isolation that profoundly affected his psychological well-being. Boltzmann's struggle intensified during the 1890s as he attempted to address criticisms of his work. One particularly challenging objection came from Poincare's recurrence theorem, which seemed to imply that any finite mechanical system would eventually return arbitrarily close to its initial state, contradicting the irreversible increase in entropy predicted by the second law of thermodynamics. Boltzmann's response to this challenge led him to consider the possibility of entropy fluctuations, introducing concepts that would later contribute to the Boltzmann Brain paradox. The tragic culmination of these struggles occurred in September 1906, when Boltzmann ended his life while vacationing near Trieste. His suicide, attributed to depression and the stress of defending his theories, occurred just as experimental evidence was beginning to vindicate his atomic hypotheses. The cruel irony of his death became apparent in subsequent decades as his statistical mechanical framework proved essential to understanding quantum mechanics, solid-state physics, and modern cosmology. The scientific vindication of Boltzmann's theories began almost immediately after his death. In 1905, Einstein's explanation of Brownian motion provided the first direct experimental evidence for the atomic nature of matter, by showing how visible particles suspended in fluid exhibited random motion caused by molecular collisions. This observation matched precisely the statistical predictions that emerged from Boltzmann's kinetic theory of gases. Jean Perrin's meticulous measurements of Brownian motion between 1908 and 1913 provided quantitative confirmation of atomic theory and allowed the first accurate determination of Avogadro's number, the quantity representing the number of particles in a mole of substance. These experiments definitively established the reality of atoms and molecules, transforming Boltzmann's theoretical constructs into empirically verified aspects of physical reality. The broader implications of Boltzmann's statistical mechanics extended far beyond vindicating atomic theory. His approach became fundamental to understanding quantum mechanics, where probabilistic descriptions of particle behavior proved unavoidable rather than merely convenient approximations. Max Planck's derivation of black-body radiation relied explicitly on Boltzmann's statistical methods, leading to the quantum hypothesis that launched modern physics. Boltzmann's definition of entropy in terms of the logarithm of microscopic states provided the foundation for information theory, connecting thermodynamics to concepts of communication and computation. This connection proved prophetic as computer science developed, revealing deep relationships between physical processes and information processing that continue to influence contemporary physics. Modern cosmology owes substantial debt to Boltzmann's insights about entropy and statistical fluctuations. His recognition that entropy could occasionally decrease through random fluctuations laid groundwork for understanding how ordered structures could emerge in an expanding universe. However, this same insight, when extended to extreme scenarios, generated the paradox that bears his name. The Boltzmann Brain hypothesis emerged indirectly from his work on entropy fluctuations. While addressing Poincaré's recurrence objection, Boltzmann noted that in a system at thermal equilibrium, random fluctuations could temporarily create regions of lower entropy, including complex organized structures. He calculated that such fluctuations could, given sufficient time, produce configurations as improbable as a room spontaneously organizing itself or gas molecules collecting in one corner of a container. Later physicists, applying similar reasoning to cosmological scenarios, realized that these fluctuations could theoretically produce arbitrarily complex structures, including conscious entities complete with false memories of past experiences. This realization created the modern Boltzmann brain paradox, where statistical arguments suggest that randomly fluctuating brains should outnumber evolved conscious beings in certain cosmological models. The irony of this development would likely have fascinated Boltzmann himself. His statistical mechanics, originally developed to explain everyday thermal phenomena like gas behavior and heat engines, ultimately generated questions about the fundamental nature of consciousness and reality. The mathematical framework he created to understand steam and ice now challenges our understanding of existence itself. Contemporary physicists recognize Boltzmann as one of the most prescient thinkers in the history of science. His statistical approach anticipated quantum mechanics by decades. His insights about entropy fluctuations informed modern cosmology, and his mathematical methods became essential tools throughout physics. The fact that his name attached to one of cosmology's most intriguing paradoxes represents a fitting tribute to a mind that consistently pushed beyond conventional thinking to reveal deep truths about the nature of physical reality. The transformation of Boltzmann's statistical mechanics from a theory about gas molecules into a framework that questions the nature of consciousness itself demonstrates the unpredictable power of scientific ideas. His mathematical description of entropy, developed to explain why steam engines work and ice melts, inadvertently provided tools for contemplating scenarios where conscious experience could arise from pure randomness. This intellectual journey from thermodynamics to existential philosophy illustrates how rigorous scientific thinking can lead to the most profound questions about reality and our place within it. Understanding Boltzmann's legacy prepares us to examine how his insights about entropy and statistical fluctuations create the foundation for one of the most challenging thought experiments in modern physics. Chapter 3. Entropy and the Arrow of Time. The universe operates according to fundamental laws that govern everything from the movement of galaxies to the decay of particles. Among these laws, one stands as perhaps the most unforgiving, the second law of thermodynamics. This principle shapes not only how energy flows through systems, but also determines why time moves in one direction and why our very existence represents such an extraordinary statistical improbability. To understand how a brain could spontaneously materialize from random particle fluctuations, we must first comprehend the force that drives all change in our cosmos: entropy. This concept will transform your understanding of why disorder reigns supreme and how rare pockets of order can emerge against overwhelming odds. Entropy represents the measure of disorder within any system, a quantification of how randomly particles and energy distribute themselves throughout space. When physicists speak of entropy, they describe a fundamental tendency that permeates every corner of reality. Consider a pristine crystal structure where each atom occupies its designated position with mathematical precision. This represents a state of extremely low entropy. The atoms maintain specific arrangements and the system exhibits clear organization. Now, observe what happens when we introduce thermal energy to this crystal. The atoms begin vibrating more vigorously, eventually breaking free from their ordered positions. As temperature increases, the crystal melts, then vaporizes, transforming from a highly ordered solid into a chaotic gas where particles move randomly in all directions. This transformation from order to disorder exemplifies entropy increase. The gas possesses far higher entropy than the original crystal because countless arrangements of particle positions and velocities can produce the same macroscopic properties we observe. In the crystal, only one arrangement maintained the ordered structure. In the gas, trillions upon trillions of microscopic configurations appear identical to our measurements. Ludwig Boltzmann provided the statistical foundation for understanding entropy through his famous equation S equals K times the natural logarithm of omega, where S represents entropy, K stands for Boltzmann's constant, and omega denotes the number of microscopic arrangements that correspond to a particular macroscopic state. This equation reveals why disorder dominates our universe. Systems naturally evolve towards states with the highest number of possible microscopic arrangements because these states are statistically most probable. A deck of cards demonstrates this principle clearly. When you open a new deck, the cards follow a specific sequence, an arrangement representing low entropy because only one microscopic configuration produces this particular order. After shuffling the deck thoroughly, you create a random arrangement. This shuffled state possesses much higher entropy because millions of different sequences would appear equally random to an observer. The probability of returning to the original ordered sequence through random shuffling approaches zero, not because any physical law prevents it, but because ordered arrangements represent such a tiny fraction of all possible arrangements. Entropy provides the arrow of time with its direction. While fundamental physical laws operate identically, whether time flows forward or backward, entropy creates an asymmetry that defines past and future. We remember the past, but cannot remember the future, precisely because our brains evolved in a universe where entropy increases consistently over time. When you drop a glass and watch it shatter on the floor, you witness entropy increase as the organized structure disintegrates into random fragments. The reverse process, fragments spontaneously reassembling into an intact glass, violates no fundamental physical laws, yet it never occurs because such an event would require an astronomical decrease in entropy. The mathematics of statistical mechanics demonstrates that while entropy can decrease temporarily in small regions through random fluctuations, these decreases become exponentially less probable as the magnitude of organization increases. A few molecules might briefly align in an ordered pattern, but the spontaneous organization of macroscopic objects remains so improbable that it effectively never happens within the lifetime of our universe. The second law of thermodynamics states that in any isolated system, entropy can only remain constant or increase, never decrease. This law ranks among the most fundamental principles governing our universe, applicable to everything from molecular interactions to cosmic evolution. Rudolf Clausius first formulated this law in the mid-19th century, recognizing that heat flows naturally from hot objects to cold objects, but never in reverse without external work. This observation led to the broader understanding that all natural processes proceed in directions that increase overall disorder. The second law explains why perpetual motion machines remain impossible. Any attempt to create a device that produces work without consuming energy violates this fundamental principle. Even the most efficient engines waste some energy as heat, increasing the entropy of their surroundings. Perfect efficiency would require entropy to remain constant, but real systems always generate additional disorder through friction, resistance, and other dissipative processes. Applied to the entire universe, the second law predicts an eventual state called heat death. As entropy increases throughout cosmic time, energy will distribute evenly across all regions of space. Temperature differences that drive stellar fusion, planetary dynamics, and biological processes will disappear. The universe will reach thermal equilibrium, a state of maximum entropy where no further work can be extracted from the system. Current observations suggest our universe contains approximately 10 to the power of 88 particles within the observable region. Each particle can occupy numerous possible states, creating an astronomical number of potential microscopic arrangements. As the universe expands and cools, it evolves toward configurations with higher entropy, driven by the statistical inevitability of disorder. This cosmic evolution shapes the formation and destruction of stars, galaxies, and planetary systems. Gravity creates local decreases in entropy by concentrating matter, but these processes generate even greater increases in entropy through nuclear fusion and radiation. The net effect always favors increasing disorder on universal scales. When a system reaches thermodynamic equilibrium, temperature, pressure, and chemical potential become uniform throughout its volume. At this point, macroscopic changes cease because no driving forces remain to produce further evolution. Particles continue moving randomly, but their statistical distributions remain constant over time. In equilibrium, entropy reaches its maximum possible value for the given constraints. This state represents the most probable configuration because it corresponds to the vast majority of microscopic arrangements. Once equilibrium is achieved, significant departures from this state become extraordinarily unlikely through natural processes. However, equilibrium does not mean perfect stillness. Microscopic fluctuations continue as particles exchange energy and momentum through collisions. These fluctuations typically involve small numbers of particles over brief time scales, causing negligible changes in macroscopic properties. Yet given sufficient time, even large fluctuations become possible, though their probabilities decrease exponentially with size. Within systems at thermal equilibrium, random particle motions occasionally produce temporary deviations from the average state. These fluctuations arise naturally from the probabilistic nature of microscopic interactions. While most fluctuations remain small and short-lived, the mathematical framework of statistical mechanics permits fluctuations of any magnitude, provided sufficient time passes. The probability of a particular fluctuation scales exponentially with the change in entropy it produces. Small fluctuations occur frequently because they require minimal decreases in entropy. Large fluctuations occur rarely because they demand substantial entropy reductions. The relationship follows Boltzmann's distribution, which quantifies how probability depends on energy and entropy changes. Consider a container of gas at uniform temperature. Most of the time, molecular motions distribute energy relatively evenly throughout the volume. Occasionally, random collisions concentrate more energetic molecules in one region, creating a temporary hot spot. This local temperature increase represents a fluctuation away from equilibrium, a spontaneous decrease in entropy that violates the second law temporarily. The mathematical theory of fluctuations reveals that their typical magnitude scales with the square root of the number of particles involved, while their duration depends on the specific physical processes governing the system. Fluctuations involving millions of molecules occur regularly but produce barely detectable effects. Fluctuations involving macroscopic quantities of matter occur so rarely that they never appear during normal observation periods. In a universe at thermal equilibrium, even fluctuations capable of forming complex structures become possible given unlimited time. The key insight is that probability never reaches exactly zero for any physically allowed configuration. Events with probabilities of 10 to the negative power of billions can and will occur if enough time passes. These rare fluctuations could theoretically produce organized structures ranging from simple crystals to intricate biological forms. The formation probability decreases dramatically as structural complexity increases, but the mathematics of statistical mechanics provides no absolute prohibition against such events. The timescales required for significant fluctuations exceed human comprehension. Creating a small organized structure through random fluctuations might require periods measured in googles of years, numbers containing more digits than atoms in the observable universe. Yet in a truly eternal universe at equilibrium, even these astronomical waiting times eventually pass. This reasoning leads to profound implications for cosmic evolution. If our universe continues expanding and cooling until it reaches thermal equilibrium, and if this equilibrium state persists indefinitely, then every possible fluctuation will eventually occur. Structures resembling anything that ever existed will spontaneously reassemble through random processes, including arrangements indistinguishable from living organisms. The probability calculations show that simpler structures form more readily than complex ones. A randomly assembled brain requires fewer particles in specific arrangements compared to an entire biosphere or galaxy. This statistical bias becomes crucial for understanding the Boltzmann Brain paradox, where isolated conscious entities emerge more frequently than the vast cosmic structures that normally support biological evolution. Quantum mechanics introduces additional sources of fluctuations beyond classical thermal motion. Even at absolute zero temperature, quantum uncertainty creates zero-point fluctuations in fields and particle positions. These quantum effects become significant in extremely dilute systems where classical thermal fluctuations approach zero. In the far future, when our universe has expanded and cooled to near absolute zero, quantum fluctuations may dominate over thermal effects. The vacuum itself exhibits quantum properties that permit spontaneous particle creation and annihilation on microscopic scales. Over vast timescales, these quantum processes could accumulate into macroscopic events. The combination of quantum uncertainty and statistical mechanics suggests that complex structures can emerge through multiple pathways. Classical thermal fluctuations might assemble particles into organized patterns, while quantum tunneling events could trigger transitions between different stable configurations. Both mechanisms contribute to the overall probability of spontaneous structure formation in equilibrium systems. Understanding these fundamental principles of entropy, thermodynamics, and fluctuations provides the scientific foundation necessary to comprehend how conscious brains might spontaneously emerge from chaos. The mathematical framework reveals why such events remain possible despite their extraordinary improbability, setting the stage for exploring whether we ourselves might represent such cosmic accidents rather than products of biological evolution. The mathematics behind entropy fluctuations reveals a startling conclusion. While the second law of thermodynamics drives the universe toward maximum disorder, the very nature of probability theory opens a door to something extraordinary. In systems where time extends beyond conventional limits, the impossible transforms into the inevitable. The concept requires us to examine a universe fundamentally different from our own, one that has reached thermal equilibrium. In such a state, matter exists at uniform temperature throughout space, with particles distributed according to the principles of statistical mechanics. No stars burn, no galaxies spiral, no complex structures persist. Yet within this apparent death lies the seed of unprecedented possibility. Thermal equilibrium represents the endpoint of cosmic evolution under traditional thermodynamic models. Every available energy has been converted to heat, and that heat has spread uniformly across all available space. The temperature differential that drives all processes, from stellar fusion to biological metabolism, has vanished. This scenario, known as heat death, marks what classical physics predicted as the universe's final chapter. However, quantum mechanics introduces a crucial modification to this classical picture. Even in perfect thermal equilibrium, particles continue to move according to quantum probability distributions. These movements are not truly random, but follow specific statistical patterns described by the Maxwell-Boltzmann distribution. Within these patterns lies the mathematical foundation for understanding how order can spontaneously emerge from chaos. The critical insight comes from recognizing that probability theory makes no distinction between likely and unlikely events over infinite timescales. An event with odds of 1 in 10 raised to the power of 1 trillion will occur given sufficient time. The formation of a functional brain from random particle interactions represents precisely such an event, vanishingly improbable over human timescales, yet mathematically certain across cosmic eternities. Contemporary calculations by physicists Andreas Albrecht and Lorenzo Sorbo demonstrate that a complete Boltzmann brain would require approximately 10 to the power of 10 to the power of 50 years to form through quantum fluctuations. This duration exceeds the current age of our universe by factors that strain comprehension. To appreciate this timescale, consider that our universe has existed for roughly 14 billion years, while a Boltzmann brain requires time periods where even the concept of billions becomes meaningless. The formation mechanism depends on the fundamental principle that quantum fields never achieve perfect stillness. Even in vacuum states, quantum fluctuations create temporary violations of energy conservation permitted by Heisenberg's uncertainty principle. These fluctuations typically last for infinitesimally brief periods and involve minimal energy. However, larger fluctuations, while exponentially less probable, remain theoretically possible. The transition from random quantum fluctuations to organized neural structure represents one of the most counterintuitive concepts in theoretical physics. Understanding this process requires careful examination of both the probability calculations and the physical mechanisms involved. A human brain contains approximately 86 billion neurons, each connected to thousands of others through an intricate network of synapses. The total number of synaptic connections approaches 100 trillion, creating a computational substrate of extraordinary complexity. Each neuron operates as a sophisticated electrochemical processor, maintaining specific ion concentrations across its membrane and responding to precise patterns of neurotransmitter release. For a Boltzmann brain to function identically to a human brain, quantum fluctuations must spontaneously arrange matter into this exact configuration. The process requires the simultaneous organization of roughly 10 to the power of 27 atoms, each positioned with sufficient precision to maintain neural function. The probability of such an arrangement occurring through random processes defies intuitive understanding. Yet the mathematics remains unambiguous. Physicist Sean Carroll's calculations demonstrate that while the formation of a single functional brain requires extraordinary improbability, creating an entire universe with consistent physical laws, billions of galaxies, and evolutionary history demands far greater improbability. The comparison reveals a troubling conclusion. In sufficiently old universes, isolated brains should vastly outnumber brains that develop through conventional evolutionary processes. The functional requirements for a Boltzmann brain extend beyond simple anatomical accuracy. The brain must emerge with neural patterns that encode specific memories, emotional responses, and cognitive capabilities. These patterns represent information content equivalent to decades of human experience compressed into synaptic configurations. The spontaneous generation of such information challenges fundamental assumptions about the relationship between entropy and information theory. Neuroscientist Christoph Koch's research on consciousness provides additional context for understanding Boltzmann brain functionality. His integrated information theory suggests that consciousness emerges from specific patterns of information integration across neural networks. A randomly generated brain, despite anatomical similarity, might lack the proper information integration patterns necessary for genuine conscious experience. The temporal existence of a Boltzmann brain introduces further complexity. Once formed through quantum fluctuation, such a brain would persist only briefly before thermal motion disrupts its delicate organization. The coherent neural activity that constitutes thought processes would continue for mere moments before the brain dissolves back into random particles. During this brief existence, the brain would experience what it perceives as a complete lifetime of memories and experiences. The mathematical inevitability of Boltzmann brain formation creates a logical paradox that strikes at the heart of cosmological theory. If these entities must exist in sufficient numbers given enough time, then statistical reasoning suggests we are more likely to be such brains than genuine biological entities with evolutionary histories. So, this conclusion emerges from straightforward probability analysis. In an infinitely old universe, the number of Boltzmann brains would eventually exceed the number of naturally evolved brains by astronomical factors. Each Boltzmann brain exists only briefly, but the sheer quantity compensates for their ephemeral nature. The mathematics forces an uncomfortable question. What evidence could distinguish our experience from that of a randomly generated brain with false memories? The paradox gains additional force when we consider observational evidence. A Boltzmann brain with artificially implanted memories would observe exactly the same universe we observe, complete with apparent histories, physical laws, and logical consistency. The brain's memories would include recollections of childhood, education, and previous observations of natural phenomena. These memories, despite being false, would feel entirely authentic to the experiencing entity. Cosmologist Andreas Albrecht emphasizes that this scenario creates what philosophers term a skeptical problem. If our memories and observations could be completely fabricated, then empirical evidence loses its power to distinguish between truth and illusion. Scientific methodology depends fundamentally on the reliability of observation and memory, yet the Boltzmann brain hypothesis suggests both could be fundamentally unreliable. The paradox extends beyond individual consciousness to challenge the foundations of scientific knowledge itself. If we are Boltzmann brains, then our scientific theories, including those that predicted our own existence, emerge from false memories rather than genuine discovery. The very calculations that demonstrate the probability of Boltzmann brain formation might themselves be products of randomly generated neural patterns rather than legitimate mathematical reasoning. Contemporary physicist Raphael Bousso argues that this paradox reveals fundamental flaws in cosmological models that predict Boltzmann brain dominance. He contends that any theory yielding such predictions should be rejected as self-defeating. If a theory implies that our reasoning about the theory is probably unreliable, then the theory undermines its own credibility. The resolution of this paradox has driven significant developments in theoretical cosmology. Modern models must satisfy what researchers call the Boltzmann Brain problem. They must predict that naturally evolved observers like ourselves significantly outnumber randomly generated ones. This requirement has influenced theories of cosmic inflation, multiverse structure, and the ultimate fate of our universe. The implications extend to fundamental questions about scientific methodology. How can we maintain confidence in empirical observation if the most probable explanation for our existence involves fabricated memories? How do we distinguish between theories that accurately describe reality and those that merely happen to match the false recollections of randomly generated minds? These questions illuminate the deep connection between cosmology and epistemology, the study of knowledge itself. The Boltzmann brain paradox forces scientists to examine not only what we know about the universe, but how we can know anything at all. The resolution requires careful consideration of both physical principles and philosophical foundations underlying scientific inquiry. The mathematical precision of these calculations, combined with their existential implications, creates a unique tension in modern physics. Numbers that seemed abstract and theoretical suddenly carry profound consequences for understanding our own reality. Whether we exist as genuine products of cosmic evolution or as fleeting fluctuations in an ancient universe becomes not merely an academic question, but a fundamental challenge to human knowledge and identity. Chapter 5. The Cosmological Conundrum. The Boltzmann Brain paradox represents one of the most intellectually demanding challenges facing contemporary cosmological theory. Scientists who dedicate their careers to understanding the universe's fundamental structure have encountered an unexpected obstacle that threatens to undermine our most sophisticated models of cosmic evolution. Our current understanding of the universe rests upon the Big Bang model, a theoretical framework that describes a cosmos approximately 13.8 billion years old. This age calculation emerges from multiple converging lines of evidence: the cosmic microwave background radiation, the observed expansion rate of space itself, and the relative abundances of light elements throughout the observable universe. The temporal constraints imposed by this relatively young cosmic age create a natural barrier against Boltzmann brain formation. When physicists calculate the probability of random particle fluctuations assembling into a functioning brain, they arrive at timescales that dwarf the current age of our universe by factors so enormous that standard mathematical notation becomes inadequate. The required waiting time approaches 10 to the power of 10 to the power of 50 years, a number that contains more digits than there are atoms in the observable universe. This temporal incompatibility initially appeared to resolve the Boltzmann brain paradox entirely. If our universe lacks sufficient age for these random assemblies to occur with meaningful frequency, then the statistical argument favoring Boltzmann brains over genuine biological observers loses its foundation. The Big Bang model seemed to provide a natural solution by constraining the available time for quantum fluctuations to produce complex structures through pure chance. However, this resolution proved temporary, as cosmologists developed more sophisticated models of cosmic evolution that extended far beyond the simple Big Bang framework. The landscape of theoretical cosmology transformed dramatically with the development of inflationary models, particularly those describing eternal inflation. These theories propose that the rapid exponential expansion characterizing the early universe continues indefinitely in most regions of space, creating an endless succession of bubble universes within an ever-expanding multiverse structure. Alan Guth, the physicist who pioneered inflation theory, demonstrated how quantum fluctuations during the inflationary epoch could generate not just one universe, but an infinite collection of causally disconnected cosmic regions. Each bubble universe experiences its own Big Bang event, develops its own physical constants, and evolves according to its own timeline. The implications for Boltzmann brain formation become immediately apparent within this framework. While our particular bubble universe remains too young for significant random fluctuations, other regions of the multiverse could have existed for arbitrarily long periods. In these ancient domains, the probability calculations that seem to prohibit Boltzmann brain formation in our universe become not only possible but statistically inevitable. Raphael Bousso, a prominent cosmologist at UC Berkeley, has extensively analyzed this problem and concluded that eternal inflation models predict Boltzmann brain observers should vastly outnumber ordinary observers like ourselves. The mathematical reasoning follows directly from probability theory. Forming a single brain through random fluctuations requires assembling fewer particles in a less complex configuration than creating an entire universe with galaxies, stars, planets, and biological evolution. This statistical argument creates what cosmologists term the measure problem in multiverse theories. If we accept that infinite time allows for infinite possibilities, then the most probable observers in such a cosmos would be randomly fluctuated brains with false memories rather than genuine biological entities with evolutionary histories. The measure problem extends beyond mere academic interest because it directly challenges the empirical foundations of cosmological theory. If our models predict that we should most likely be Boltzmann brains, yet we observe a consistent, structured universe with reliable physical laws, then these models appear to contradict the very evidence we use to construct them. Sean Carroll, a theoretical physicist at Caltech, has articulated the most devastating critique of cosmological models that predict Boltzmann brain dominance. His argument centers on the concept of cognitive instability, the idea that theories leading to unreliable observations undermine their own epistemic foundations. The logical structure of Carroll's argument proceeds as follows. If cosmological theories predict that we are most likely Boltzmann brains with false memories, then our observations of cosmic microwave background radiation, supernova distances and galactic structure could represent nothing more than random neural activity in a fluctuated brain. These apparent observations would contain no genuine information about the universe's actual properties. This creates a self-defeating scenario where the very evidence supporting a cosmological theory simultaneously becomes unreliable if that theory predicts Boltzmann brain dominance. Scientists cannot simultaneously maintain confidence in observational data and accept theories that classify those observations as probable illusions. Carroll demonstrates that this cognitive instability criterion provides a powerful tool for evaluating cosmological models. Theories predicting that typical observers are Boltzmann brains fail this test because they render scientific observation epistemologically meaningless. The scientific method itself depends upon the assumption that our perceptions correspond at least approximately to external reality. The implications extend throughout theoretical physics. String theory models with numerous vacuum states, eternal inflation scenarios with infinite space-time volumes, and cyclic cosmological theories all face potential rejection if they lead to Boltzmann brain dominance. This criterion has already influenced the development of new theoretical approaches that explicitly avoid this pathological prediction. Some physicists argue that cognitive instability represents an overly restrictive constraint on theoretical speculation. They contend that dismissing otherwise successful theories, based solely on their implications for observer statistics, may prematurely close off promising research directions. However, the majority of cosmologists now accept that theories must remain consistent with the reliability of scientific observation to maintain their empirical relevance. The Boltzmann Brain paradox thus forces cosmologists to confront fundamental questions about the relationship between theoretical prediction and empirical validation. Models that successfully explain observed phenomena while simultaneously predicting those observations should be illusions create an unprecedented challenge for scientific methodology. Resolving this tension requires either developing new theoretical approaches that avoid Boltzmann brain dominance or fundamentally reconsidering the role of observer selection in cosmological theory. Chapter 6. Resolving the Paradox. The Boltzmann Brain paradox presents a fundamental challenge to our understanding of cosmology, but if these spontaneous brains are statistically more probable than our entire ordered universe, then our very existence becomes mathematically suspect. This conclusion threatens the foundation of scientific reasoning itself, forcing physicists to confront an uncomfortable question: how can we trust our theories if they predict we shouldn't exist? The scientific community has responded to this challenge with characteristic rigor, developing multiple theoretical frameworks that preserve both mathematical consistency and observational reality. These solutions demonstrate how science adapts when faced with apparently insurmountable contradictions. The most direct approach to resolving the Boltzmann brain paradox involves modifying our models of cosmic evolution. Theoretical physicists have identified specific scenarios where the formation of these random observers becomes negligible compared to normal biological evolution. Consider a universe with a finite lifespan. If our cosmos undergoes complete decay within approximately 20 billion years, the timescales required for significant Boltzmann brain formation never materialize. The vast temporal epochs necessary for random fluctuations to produce conscious entities simply do not exist. Current models of proton decay, while still speculative, suggest that even the most stable atomic nuclei will eventually disintegrate. This natural endpoint to cosmic history eliminates the infinite time periods that make Boltzmann brains statistically inevitable. Sean Carroll and his colleagues have demonstrated that vacuum decay provides another resolution mechanism. In quantum field theory, our current vacuum state may be metastable rather than truly stable. If this apparent stability represents a false minimum in the cosmic energy landscape, then catastrophic decay becomes inevitable. When this transition occurs, it propagates at the speed of light, obliterating all existing structure, including any potential Boltzmann brains. The bubble of true vacuum expands outward, resetting the cosmic environment before random fluctuations can produce significant numbers of conscious observers. Alternative cosmological models propose cyclical universes that avoid the problem entirely. In these frameworks, periods of expansion and contraction prevent the system from reaching the thermal equilibrium necessary for Boltzmann brain dominance. Each cycle refreshes the cosmic order, maintaining the low entropy conditions that favor normal observer formation over random fluctuations. Multiverse theories present more sophisticated mathematical solutions. Raphael Bousso and other theoretical physicists have developed measure problems that weight different types of observers according to specific criteria. These measures prioritize observers who emerge through causal processes over those arising from pure chance. The mathematics becomes complex, involving the relative probability of different universe types and their observer populations, but the underlying principle remains clear. Normal observers like ourselves receive higher statistical weight than random brains. The holographic principle offers yet another avenue for resolution. This theoretical framework suggests that all information contained within a volume of space can be represented on its two-dimensional boundary. Under holographic constraints, the formation of Boltzmann brains requires exponentially more resources than previously calculated, making them far less probable than conventional cosmological models predict. Empirical evidence plays a crucial role in evaluating cosmological theories. Our consistent observations of an ordered universe provide powerful constraints on theoretical models. If we truly existed as Boltzmann brains, our memories and perceptions would be fundamentally unreliable. Random neural configurations would produce chaotic, inconsistent experiences rather than the coherent reality we observe. The scientific method itself depends on reproducibility and consistency. Experiments conducted by different researchers at different times yield identical results. This reproducibility contradicts the random nature expected from Boltzmann brain observations. Each random brain would possess different false memories and would perceive different versions of physical laws. The universal agreement on fundamental constants and experimental outcomes provides strong evidence against the Boltzmann brain hypothesis. Modern cosmology relies on multiple independent lines of evidence. Observations of cosmic microwave background radiation, supernovae distances, and large-scale structure formation all point toward a consistent cosmological model. These diverse measurements, conducted using different instruments and methodologies, converge on the same description of cosmic evolution. Random brains would not produce such coherent, mutually supporting datasets. The anthropic principle guides our interpretation of these observations. We observe a universe compatible with our existence not because of random chance, but because we necessarily inhabit a cosmos capable of producing observers like ourselves. This selection effect explains why we find ourselves in a universe with appropriate physical constants, an evolutionary history without invoking improbable fluctuations. Cognitive stability provides an additional observational constraint. Our ability to reason consistently about the universe, develop predictive theories, and build upon previous knowledge demonstrates a coherent relationship between mind and reality. Boltzmann brains, possessing random neural configurations, would lack this stability. Their thoughts would be inconsistent and their memories unreliable, preventing the cumulative progress that characterizes human scientific understanding. The correlation between different observers strengthens this argument. Independent human researchers reach similar conclusions when studying the same phenomena. This agreement would be impossible if we were random brains with fabricated memories. The convergence of scientific understanding across cultures and centuries supports the reality of our shared cosmic environment. The contemporary physics community has reached a provisional consensus regarding the Boltzmann brain paradox. Leading cosmologists now agree that any viable theory of the universe must avoid predicting the dominance of random observers. This requirement has become a standard criterion for evaluating cosmological models. Brian Greene represents this mainstream position when he expresses confidence that we are not Boltzmann brains. He views the paradox as a mathematical puzzle, requiring resolution, rather than a genuine threat to our understanding of reality. This perspective reflects the broader scientific conviction that our observations provide reliable information about the actual universe. Current lambda CDM cosmology, the standard model of Big Bang cosmology, naturally avoids Boltzmann brain problems. Our universe's age of 13.8 billion years provides insufficient time for significant random brain formation. The ongoing expansion and cooling of space maintains the low entropy conditions necessary for normal structure formation while preventing the thermal equilibrium that would enable spontaneous consciousness. Inflationary cosmology, while more complex, also incorporates mechanisms that suppress Boltzmann brain formation. Eternal inflation models that initially appeared problematic have been refined to include measures that prioritize normal observers. These theoretical developments demonstrate how scientific frameworks evolve to maintain consistency with empirical evidence. String theory approaches to cosmology similarly incorporate Boltzmann brain constraints. The landscape of possible string vacua includes configurations that avoid the paradox while maintaining mathematical consistency. These models suggest that our observed universe represents one of many possible solutions to the fundamental equations of physics. Dark energy research has particular relevance to Boltzmann brain formation. The accelerating expansion of our universe, driven by dark energy, determines the ultimate fate of cosmic evolution. Current models suggest that this acceleration will continue indefinitely, preventing the thermal equilibrium necessary for significant random brain production. The precise value of the cosmological constant appears fine-tuned to avoid both immediate cosmic collapse and eventual Boltzmann brain dominance. Quantum gravity theories provide additional frameworks for resolution. Loop quantum cosmology and other approaches suggest that quantum effects prevent the extreme conditions necessary for thermal equilibrium. These theories naturally incorporate mechanisms that maintain cosmic evolution without reaching the stagnant states that enable random observer formation. The resolution of the Boltzmann brain paradox demonstrates the self-correcting nature of scientific inquiry. When theoretical predictions conflict with observational reality, physics develops new models that preserve both mathematical rigor and empirical accuracy. This process reflects the fundamental commitment of science to maintaining consistency between theory and observation. Modern cosmology therefore provides multiple pathways for avoiding Boltzmann brain dominance while preserving our understanding of cosmic evolution. These solutions range from finite universe models to sophisticated multiverse measures, each offering mathematical frameworks that align theoretical predictions with observational evidence. The convergence of these diverse approaches strengthens our confidence that we exist as genuine observers, in an authentic cosmos rather than as fleeting fluctuations in an empty void. Chapter 7. Reality, Consciousness and Existence. We stand at the precipice of understanding, yet the ground beneath our feet remains uncertain. The Boltzmann brain hypothesis has guided us through the labyrinth of physics and probability, but now we must confront questions that extend beyond equations and statistical mechanics. What emerges is not merely a scientific curiosity, but a profound challenge to the very foundations of human experience. The mathematics may reassure us that we exist as genuine observers in an authentic universe, yet the philosophical implications refuse to dissolve into comfortable certainty. Every conscious moment you experience, every memory you cherish, every sensation that confirms your existence, all of these could theoretically emerge from the random dance of particles in an empty cosmos. This possibility transforms our investigation from an academic exercise into an existential inquiry that strikes at the core of human consciousness. When philosophers and scientists speak of reality, they invoke concepts that most people accept without examination. You wake each morning assuming the world exists independently of your perception, that your memories accurately reflect past events. and that other conscious beings share your experience of existence. The Boltzmann Brain hypothesis shatters these assumptions with surgical precision. Consider the fundamental question: what constitutes authentic existence? Traditional philosophy has grappled with this problem for millennia, but the Boltzmann brain adds a quantitative dimension that transforms abstract speculation into concrete probability calculations. If random fluctuations can generate a brain complete with false memories of childhood, education, relationships and experiences, then the distinction between genuine and illusory existence becomes meaningless from the perspective of the experiencing subject. This scenario resonates with solipsism, the philosophical position that only one's own mind can be known to exist with certainty. The 18th century philosopher George Berkeley argued that material objects exist only as perceptions in minds, leading to his famous dictum, esse est percipium, to be is to be perceived. The Boltzmann brain hypothesis presents a cosmic variation of this theme. Your entire perceived universe, including other people, historical events and scientific knowledge, might exist solely as neural patterns in a brain that emerged from quantum foam. The implications cascade through every aspect of human understanding. Your scientific education, your grasp of physics, your knowledge of Ludwig Boltzmann himself, all could be fabricated memories embedded in a randomly assembled cognitive structure. The very concept of the Boltzmann brain that you are now contemplating might be nothing more than an emergent property of chaotic particle interactions. Contemporary philosophers like Nick Bostrom have proposed the simulation hypothesis, suggesting we might be conscious entities within a computer simulation created by an advanced civilization. This idea shares striking parallels with the Boltzmann brain scenario, yet important distinctions emerge upon closer examination. A simulation requires deliberate creation by intelligent agents with specific goals and computational resources. In contrast, a Boltzmann brain needs no designer, no purpose, no infrastructure, only the blind probability of particle arrangements in an ancient universe. Both hypotheses challenge our epistemic confidence, yet they do so through different mechanisms. The simulation hypothesis suggests our experiences are artificial but purposefully created, while the Boltzmann brain implies our experiences are artificial and entirely accidental. This distinction affects how we might evaluate evidence for our authentic existence. Neuroscientist David Chalmers identified what he termed the hard problem of consciousness, explaining how and why physical processes give rise to subjective experience. This problem becomes particularly acute when considering Boltzmann brains. If consciousness emerges from specific patterns of neural activity, as materialist theories suggest, then a randomly formed brain with identical patterns should theoretically produce identical conscious experiences. Yet this conclusion troubles many philosophers and scientists. Consciousness might require more than mere pattern matching. It could demand developmental history, embodied interaction with environment, or evolutionary context that shapes neural architecture over time. A Boltzmann brain lacks this biographical foundation, raising questions about whether its experiences would possess the same qualitative character as human consciousness. The debate between internalist and externalist theories of consciousness becomes crucial here. Phenomenal internalism argues that conscious experiences depend only on internal brain states, regardless of how those states arose. Under this view, a Boltzmann brain with neural patterns identical to yours would have experiences indistinguishable from your own, including the sense of being a real person with genuine memories. Phenomenal externalism, however, maintains that conscious experiences necessarily involve relationships between the brain and external world. Consciousness emerges through causal interactions with environment, social context, and evolutionary pressures. From this perspective, a Boltzmann brain might produce neural firing patterns but fail to generate authentic conscious experience because it lacks the proper causal history and environmental embedding. The explanatory gap between physical processes and subjective experience becomes a chasm when confronting Boltzmann brains. Even if we could precisely map every neural connection in a randomly formed brain and confirm its structural similarity to human brains, we would still face the fundamental question: is there something it is like to be this brain? Does it experience the redness of red, the pain of loss, the joy of discovery? This uncertainty extends to our own consciousness. If we cannot definitively determine whether a Boltzmann brain experiences subjective states, how can we be certain of our own conscious experiences? The problem becomes recursive. Our confidence in our own consciousness depends partly on our understanding of consciousness itself, yet that understanding might be comprised of false memories in a randomly formed brain. Human consciousness evolved through millions of years of natural selection, shaped by survival pressures, social interaction, and environmental challenges. Our cognitive architecture reflects this history. We possess emotional responses calibrated to ancestral environments, perceptual systems tuned to detecting relevant stimuli, and reasoning capabilities that enhance reproductive success. A Boltzmann brain lacks this evolutionary foundation. Its neural patterns might simulate human responses, but those patterns would lack the deep functional integration that characterizes evolved consciousness. The question becomes whether consciousness requires this evolutionary scaffolding or whether it emerges purely from neural organization regardless of origin. Faced with the possibility that our entire existence might be a cosmic accident, how should rational beings respond? The question transcends academic philosophy and enters the realm of practical ethics and meaning-making. Even if we cannot achieve absolute certainty about our ontological status, we must navigate daily life with limited information and probabilistic reasoning. The scientific response emphasizes methodological confidence over absolute certainty. Our best cosmological models suggest that we inhabit a young universe where Boltzmann brains remain statistically negligible. This conclusion relies on empirical observation, mathematical modeling, and theoretical consistency. The same tools that have revealed the structure of atoms, the expansion of space, and the evolution of stars. While we cannot eliminate all doubt, we can establish reasonable confidence in our genuine existence. Regardless of whether we are Boltzmann brains or evolved biological entities, the experience of consciousness carries inherent value and meaning. The philosophical question becomes whether meaning depends on ontological authenticity or emerges from the structure of experience itself. If a Boltzmann brain experiences love, creativity, curiosity, and wonder, do these experiences lose significance because of their random origin? Some philosophers argue that meaning-making is an intrinsic feature of conscious experience, independent of causal history. Others maintain that authentic meaning requires genuine relationships, real achievements, and objective foundations. This debate reflects deeper questions about whether value is discovered or created, whether purpose requires external grounding or emerges from internal commitment. The Boltzmann brain hypothesis exemplifies the scientific spirit at its most profound. Science demands that we follow reasoning wherever it leads, even when conclusions challenge our most basic assumptions about existence. The hypothesis emerged not from philosophical speculation, but from rigorous application of thermodynamic principles and probability theory. That these calculations produced such unsettling implications testifies to the power and integrity of scientific methodology. This intellectual courage, the willingness to confront uncomfortable possibilities, distinguishes scientific thinking from dogmatic certainty. Science progresses by testing ideas against observation, discarding failed theories, and refining successful ones. The fact that contemporary cosmology has largely resolved the Boltzmann brain problem demonstrates this process in action, showing how scientific reasoning can address even the most fundamental challenges to human knowledge. Perhaps the most appropriate response to the Boltzmann brain hypothesis is neither dismissive certainty nor paralyzing doubt, but rather intellectual humility coupled with practical engagement. The universe contains mysteries that may forever exceed human comprehension, yet this limitation need not prevent meaningful investigation and purposeful action. The hypothesis reminds us that consciousness itself remains deeply mysterious. We do not fully understand how subjective experience emerges from neural activity, how memories form and persist, or how meaning crystallizes from the interaction between mind and world. These gaps in knowledge create space for wonder, investigation, and discovery. The Boltzmann brain hypothesis ultimately serves as a mirror, reflecting our deepest questions about existence, consciousness, and reality. While the mathematical analysis suggests we are not cosmic accidents but genuine products of a structured universe, the philosophical questions persist with undiminished force. What does it mean to be real? How does consciousness relate to physical processes? Can meaning exist without certainty? These questions lack definitive answers, yet their exploration enriches human understanding and expands our conception of what it means to exist as conscious beings in a vast cosmos. The Boltzmann brain may be a statistical improbability, but it has generated profound insights into the nature of mind, reality, and scientific reasoning. In confronting the possibility of our own illusory existence, we have discovered new depths in our appreciation for consciousness, meaning, and the remarkable fact that the universe has evolved structures capable of contemplating their own existence. The journey through the Boltzmann brain hypothesis reveals that some of our most cherished assumptions about reality rest on foundations more fragile than we might have imagined. Yet this fragility need not inspire despair, but rather a deeper appreciation for the extraordinary phenomenon of conscious experience, however it might have emerged from the quantum foam of possibility. Conclusion. Current cosmological models provide substantial reassurance that we exist as authentic biological entities rather than random quantum fluctuations. The mathematics favors our reality. Young universe theories, finite cosmological lifespans, and refined multiverse measures collectively indicate that Boltzmann brains remain statistical curiosities rather than dominant observers. Sean Carroll's cognitive instability argument demonstrates why theories predicting Boltzmann brain prevalence must be rejected on logical grounds. Brian Greene's confidence in our genuine existence reflects the broader scientific consensus that has emerged through rigorous theoretical analysis. Yet this scientific resolution carries important limitations that demand acknowledgement. The confidence we possess stems from mathematical models and theoretical consistency rather than direct empirical verification. We cannot perform controlled experiments on cosmic scales or observe alternative universes to validate our conclusions. The reassurance that science provides operates within the framework of methodological naturalism, assuming that consistent mathematical relationships reflect underlying physical reality. Science has addressed the probability calculations underlying the Boltzmann brain paradox, but profound philosophical questions remain unresolved. The nature of consciousness itself continues to elude complete scientific explanation. We possess detailed knowledge of neural architecture, electrochemical signaling, and cognitive processing, yet the emergence of subjective experience from objective physical processes remains mysterious. This explanatory gap becomes particularly significant when considering whether randomly assembled neural patterns could generate authentic conscious experience. The problem of other minds, recognized by philosophers for centuries, acquires new dimensions in light of the Boltzmann Brain hypothesis. You can never directly access another being's conscious experience to verify its authenticity. This limitation applies equally to biological humans and hypothetical Boltzmann entities. The external behavioral evidence that we typically use to infer consciousness in others could theoretically be replicated by any sufficiently complex information processing system, regardless of its origin or underlying substrate. Memory and personal identity present additional complications that resist simple resolution. Your sense of continuous selfhood depends critically on memory systems that you cannot independently verify. Every recollection of your past, every learned fact, every emotional association that contributes to your identity could theoretically be false information embedded in neural patterns. The circular nature of this problem becomes apparent when you recognize that even your understanding of memory formation and personal identity might itself constitute false knowledge. The Boltzmann Brain hypothesis has fundamentally altered how cosmologists evaluate theoretical proposals. Modern theories must now pass what we might call the observation selection test. They must explain why we observe an ordered universe with consistent physical laws, rather than a chaotic environment dominated by random fluctuations. This requirement has led to refinements in inflationary cosmology, modifications to eternal inflation models, and new approaches to multiverse theory that prioritize normal observers. This transformation represents a significant shift in scientific methodology. Traditionally, physicists developed theories based on mathematical elegance, empirical adequacy, and predictive success. The Boltzmann Brain problem has added an anthropic constraint. Successful theories must explain not only what we observe, but also why we exist as observers capable of making those observations. This requirement forces scientists to consider the relationship between physical laws and conscious experience in ways that were previously unnecessary. The hypothesis has also highlighted the importance of measure problems in cosmology. When dealing with infinite or very large populations of observers, the method used to compare different types of observers can dramatically affect conclusions about their relative abundance. These measure problems reveal that even sophisticated mathematical frameworks can yield ambiguous results when pushed to their logical extremes. The Boltzmann Brain hypothesis compels us to examine our most basic assumptions about existence and knowledge. The simple fact that you can coherently contemplate your own potential non-existence as an authentic entity reveals something profound about the nature of consciousness and self-reflection. This capacity for metacognitive analysis, thinking about thinking itself, emerges as a remarkable feature of complex information processing systems, whether they arise through biological evolution or random quantum events. The hypothesis also illuminates the relationship between knowledge and existence. Every piece of information you possess about the world, including scientific knowledge, historical facts, and personal memories, could theoretically be false. Yet this possibility does not invalidate the internal consistency and functional utility of your knowledge systems. A Boltzmann brain with false memories of studying physics would still possess information structures that enable mathematical reasoning, logical inference, and scientific analysis. The pragmatic value of knowledge might persist independent of its correspondence to external reality. This recognition leads to questions about the foundations of meaning and value. If conscious experience possesses intrinsic significance, then that significance might not depend on the causal history that produced the experience. A Boltzmann brain experiencing wonder at the beauty of mathematics, love for others, or curiosity about the universe might generate authentic meaning despite its accidental origin. Alternatively, meaning might require genuine relationships, real achievements, and objective foundations that random fluctuations cannot provide. The Boltzmann brain hypothesis serves as a powerful reminder that consciousness remains the deepest mystery in science and philosophy. We have identified neural correlates of consciousness, mapped the brain's information processing capabilities, and developed sophisticated theories of cognitive function. Yet the fundamental question of why there is subjective experience at all, why there is something it is like to be a conscious entity, continues to resist scientific explanation. This mystery extends beyond questions of mechanism to questions of distribution and boundaries. Which physical systems possess conscious experience? Do simple information processing systems have rudimentary forms of consciousness? Could quantum computers or advanced artificial intelligence systems develop subjective experiences? The Boltzmann brain hypothesis highlights these questions by proposing a scenario where complex neural patterns arise without evolutionary development or biological constraints. The integrated information theory proposed by Giulio Tononi attempts to quantify consciousness based on the amount of integrated information that a system generates. Under this framework, a Boltzmann brain with appropriate neural architecture could theoretically possess consciousness equivalent to a biological brain with identical information integration patterns. Other theories, however, emphasize the importance of causal history, environmental interaction, or evolutionary development in producing genuine conscious experience. The Boltzmann brain hypothesis exemplifies what we might call the scientific sublime, the capacity of scientific reasoning to generate ideas that simultaneously inspire awe and intellectual vertigo, like standing at the edge of a vast canyon or contemplating the scale of cosmic space and time. Considering the possibility of our own non-existence as authentic entities produces a distinctive emotional and intellectual response that combines wonder with unsettlement. This sublime quality emerges from the rigorous application of logical reasoning to its ultimate conclusions, regardless of where those conclusions lead. The scientists who developed the Boltzmann brain hypothesis were not seeking to undermine human confidence in existence, but rather following thermodynamic principles and probability theory to their logical endpoints. The disturbing implications arose naturally from careful analysis rather than deliberate provocation. The resolution of the paradox through improved cosmological models demonstrates the self-correcting nature of scientific inquiry. When theoretical predictions conflict with empirical observations or logical consistency, the scientific method demands revision and refinement. The Boltzmann brain problem has catalyzed important advances in cosmological theory, leading to better understanding of universe evolution, observer selection effects, and the relationship between physical laws and conscious experience. Perhaps the most important lesson from the Boltzmann brain hypothesis concerns the provisional nature of human knowledge and the appropriate response to fundamental uncertainty. Science provides our best current understanding of reality, but this understanding remains subject to revision as new evidence emerges and theoretical frameworks evolve. The confidence we possess in our authentic existence rests on probabilistic reasoning and theoretical consistency rather than absolute certainty. This recognition need not lead to paralysis or despair, but rather to intellectual humility and continued curiosity. The universe contains phenomena that may forever exceed human comprehension, yet this limitation creates opportunities for discovery, wonder, and meaning-making. The fact that consciousness emerged in the universe, whether through evolutionary processes or quantum fluctuations, represents an extraordinary development that deserves appreciation regardless of its ultimate causal origins. The Boltzmann Brain hypothesis ultimately expands rather than contracts our conception of what it means to exist as conscious beings in a vast cosmos. By forcing us to question our most basic assumptions about reality and consciousness, it opens new avenues for investigation and understanding. The journey through this conceptual landscape reveals that some of our deepest questions about existence, meaning, and consciousness remain beautifully, mysteriously unanswered. In facing the possibility of our own cosmic insignificance, we discover new appreciation for the remarkable phenomenon of conscious experience and the ongoing human quest to understand our place in the structure